This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Make a start. Today we are going to be focusing on what are called synchronous reactive models. This is going to solve our feedback problem when we looked at composition, concurrent composition beforehand. I'll just point out that the reference for this is Chapter 6.2 and 6.1, which is a sort of an intro into 6.2, and we're not going any further into Chapter 6. So Chapter 6.3 onwards has data flow models and some complex timing stuff. We don't need to cover that, okay? So read ahead if you're really interested in the text, but 6.2 is where we're stopping in Chapter 6. Okay, so I'm going to preempt Wednesday's lecture on multitasking by telling you that threads, or some sort of idea of multitasking, is really bad for embedded systems. Embedded systems, we want predictable behaviour, we want timing to be analysable and everything neatly able to be predicted. Where we have things like multitasking and threads, it makes things very difficult to deal with. Okay, so I'll come back to this point at the end of the lecture. We've already seen it anyway when we looked at interrupts, and interrupts allowing jumping to bits of code that can alter other things that are happening inside a computer system or an embedded system. Right, but today what we're going to focus on is feedback composition. Okay, so we've already seen side-by-side composition with state machines, cascade composition, and we've seen state refinement. So being able to have an OR model, basically, of a state machine where if you're in, say, state B, you're either in C or D, right? And that's called state refinement, a hierarchical state machine. But we are going to today focus on synchronous composition, in particular for feedback. So just as a reminder, you can combine two state machines in side-by-side composition where their inputs and outputs are independent of each other, but we can lump them together so that you have now a set of inputs and a set of outputs across the two machines. And we can do that two ways, synchronously or asynchronously. And remember, if we had these things reacting asynchronously, we then had to determine some semantics about who is allowed to react and what the reaction process is. So we've got A and B as state machines, and we have to make a choice. Do we allow A, do we allow B, or do we allow both of them to react at the same time for asynchronous side-by-side composition? And we fell into the semantics which makes sense about interleaving. So basically, we either B or A react, but not both. And that led us down a complex path of non-deterministic state machines with those red arrows, because we couldn't determine which machine reacted. So in the composition, we have to show both possibilities happening. Now, for synchronous composition, it's much simpler because we have a deterministic composition in that on some event of the system or environment, like a tick of a clock, right, these machines both react in lockstep. So they transition to different states, evaluate the guards, and react together at the same time in lockstep. And you can think of that again as, you've got a common clock signal or something going to these to tell these machines when to react. For cascade composition, synchronous composition still implies that both machines react simultaneously and instantaneously in lockstep again, despite them looking like there's some sort of flow of information going on here, that there's a causal relationship. Okay, typically when you model systems, maybe in signals and systems and things like that, it looks like the result of A has to be known before B. Okay, you've got to process A before you can process B, because the output of A is the input of B. But that's not, that's not so. Okay, and I'll show you why on the next couple of slides. In terms of asynchronous composition, if you want to asynchronously compose things in cascade, it gets very messy because you're allowing A, B to react in arbitrary order, right? If we have interleaving semantics here, then we could have missed information, basically. Okay, so for instance, if there was a reaction on the overall state machine here, so a reaction on the input, but you only allowed B to react for that particular input, then you may miss information because this state machine hasn't reacted. Right? In asynchronous composition, you've got to choose one of the machines to react, one of the sub-machines to react. Okay, so asynchronous composition for this is very difficult. You essentially might need some buffering system here to make sure you don't miss, or buffering on the inputs to make sure you don't miss information. It's messy and we won't consider it. To show you what, even though that there's this cascade connection, that we don't consider an apparent causal relationship between these two things, here are two very simple state machines. In fact, they're exactly identical in terms of their FSM diagrams here, their update behaviour. They've just been enumerated with different outputs and inputs and different state names. So if we've got a cascade composition and we want to cascade them synchronously, then we just have to, we know that they both react at the same time. We have to enumerate all the possible input-output cases. Okay, so for instance, right, we know that both of the machines will default to an S1, S3 state. Once again, remember, if we've got two machines with two states in them, that the product of the state space, if you like, is going to be 4 states. It's going to be S1, S3, S1, S4, S2, S3, S2, S4. We may have unreachable states, which we can later remove, but the worst case is the composition of these two is the product of the state spaces of both of these systems. Okay, so we have to perform the composition S1, S3, S1, S4, S2, S3, S4, and determine the reactions between all of those different composed states. So we might show it this way, that obviously the state space of the composition is the cross of the spaces of both of the state spaces, the independent, separate machines. And we start off at our default state and we enumerate all the possible reactions that can occur and what states they go to. So it's really like a search sort of space that you go over in order to compose these machines. So we know we start here. So we're in S1, S3. The simple one here is that if A is present, so A is the input here on the left, if A is present, then we stay in S1 and we output B. Now, simultaneously, while we're thinking about that, over in this state machine, B being the input, so B is present. If B is present, we output C being present. So that leads to our little transition, if you like, or loop back here of if A is present, then C is present on the output. So that's composed these two states and taken into account the self loops there. What else can happen? Well, if A becomes absent, then machine A transitions to S2. And the output goes from being present to being absent. Now, because B is this internal signal in here, right, it's also the input to this machine, we have to, at the same time, work out how machine B reacts, right? So at the instant where A becomes absent, right, the output of this becomes absent, and if we're in S3, an absent input B leads us to a transition to S4 with an absent output. So all that together is this little transition here. That A being absent has simultaneously made both machines move across to their other states, S2, S4, in lockstep. Now, if we're in S2, S4, then both of these guards are true, so we just have always a true transition here with no output, so the output's absent here. Remember once again that this has no concept of timing here. So when is this transition taken? Well, it's always taken. When is it taken? The environment decides, okay? By environment, master clock signal, whatever, something will tell it when to go. That's where it will go. Now, obviously, if we've enumerated both possibilities out from S1, S3, the default states, then that's essentially it in terms of reachability, right? We can check the other two possible combinations of states here, and if somehow we ended up in those, you can enumerate the transitions here in and out of the states. Note that if you ever ended up in S1, S4, right, the presence of A will pull you back to the default two states, and then you end up basically inside here. Okay, so we determine that these two states are unreachable. There's no entry transition into either of those. And luckily, if you like, if we ended up in either of those, we would eventually probably, as long as A is present at some stage, fall back to our ordinary little state machine here. Okay, so putting these together, it's, you know, it can be a little bit tedious because you've got to enumerate all possibilities. The only tricky part is that you must remember that, for instance, this transition here, when A is absent, right, because you've got this interconnection, that this needs to react at the same time, right? They're synchronously reacting. Okay, if you thought of it as that causal relationship that A has to be reacting before B, well, they're not synchronous, And what that then means is that you then end up with the unreachable states being able to be reached. Okay, you end up like in a synchronous composition again. Okay, that's all well and good. The real problem occurred when we looked at feedback. Now, how feedback differs is that a subset of the outputs of the machine here are then fed back into the machine itself. And we avoided that problem. We kind of just said, we'll just think about it later, and now we're going to think about it. And it leads us down a difficult path to traverse. We have to define some things very carefully. Okay, so think about this machine here, right? In order for it to react here, right, and it's got, all of its states, inputs, outputs, the update function, and an initial state. In order for it to react, right, we need to know its inputs. And in order to determine its outputs, we need to know the state it's in and its inputs. But we've got a problem, right? We need to know the inputs in order to determine the outputs, but we need to know the outputs because the outputs are the inputs, or a subset of them anyway. So we've got a problem. Now, note that if this machine in particular was what's called a Moore machine, this wouldn't necessarily be a problem. Why is that? A Moore machine is a very simple type of FSM. It's where the output is only dependent on the state. Okay, the update function still depends on the inputs, right? You choose where to go on the FSM diagram, but the output is purely just dependent on the state you're in. Where it falls down is for a more general Mealy machine, and a Mealy machine, the output depends not only on the states, but the inputs as well. And that's where this model causes big problems, the feedback model for Mealy machines. Okay, more general Mealy machines. Okay, so what we want some sort of framework, formalism, to say that if we were given the transition diagram of this, and we knew the spaces of input-output signals here, we would want to be able to make a statement to say that this composition will work. What do I mean by work? That it will... We'll define what work means, but that it will behave properly. Okay. It turns out, actually, funnily enough, that any composition, non-trivial composition, is a feedback composition. That's kind of a bummer because we thought that this was a special case, right? That it's only when you get feedback like this where you have to start thinking about timing in particular. So here's an example. If you start off at A, and maybe what I might do is I might actually... So ignore the stuff on the right for the moment. So we've got 3 actor models here, and they're interconnected via some ports in the following way. We've got a sort of a cascade connection between these two. We've got a feedback connection here, and another cascade between F1 and F2. Obviously, you can redraw this diagram just by shuffling around those blocks, and you end up with something that looks like this. And you note that we can abstract the 3 actors together into a composition. Okay? Right? So we can look at these as side-by-side composition. Right? They're just sitting there. They've got inputs, they've got outputs. And the interconnection is then the 3 signals that are floating around here that perform feedback. So if we abstract the actors together in a side-by-side composition, and then we abstract the signals together by sort of stacking them together, right? Remembering that there are independent signals here, then we end up with a feedback interconnection. Okay, so we have F being the actor model of the abstraction of these 3, and then this mysterious signal we're going to call S. Now, this defines an interesting relationship, that if S, and S is now, it can be a multi-dimensional signal, right? Clearly it is here, right? It's 3 of them. So we're saying it's multi-dimensional in a signal space. Clearly, this is a relationship that F acting on S has to give me S. Clearly, right? It shows you that the F acting on the input gives you an output that is the input. And we call this a fixed point. In order for this to make sense, this must hold. Yeah? The actors, the abstracted actor, whatever you want to call it, but the actors here acting on the signal S must give you back S. We call it a fixed point. We'll do some concrete examples with this. So we need it to be fixed. We need it, or a fixed point, we need it to exist, right? And we need it to be unique. And I'll give you some counter examples for that. And we would like a constructive procedure to find it. Why? Because we really want to work out what the overall behaviour of that feedback interconnection is, right? So we need a constructive procedure to find fixed point and make sure that it exists and it's unique. And therefore that is then the behaviour of the system. All right. Now, just before we embark down this process of exploring what this fixed point is, we have to be a bit careful about the types of signals as well. So, and this is a bit more formalism. It's probably, I mean, you can summarise this entire slide with apples have to be apples and oranges have to be oranges, basically. The space, remember, these could be multiple signals here, right? But the space of output signals here is a subset or equal to the full set of input signals here. And that kind of, I hope it sort of makes sense in that if you think about the acceptable input signals here, right, being space of signals, that Vy has to be a subset of the allowable input signals. Kind of makes sense. It can't be the other way around. So this signal here on the feedback here is a mapping, right? And we're talking synchronous systems now, so forget about T being R. So forget about being a real number, right? It's no analog time base, if you like, right? These are discrete events, so natural numbers. The domain of this is natural numbers, and the codomain is now the space of output signals unioned with absent, because, well, there may be no event there as the signals. And so what's Vy? Well, Vy could be lots of things. It could be just a pure signal, right? Py, present absent. It could be natural numbers. It could be anything, right? So it's whatever that signal space is unioned with absent. Okay, so fixed point says we've got to find an S such that this can hold, that the actor model on the signal gives you back the signal itself. Okay, but this is the actor function, and this is where it gets a little pedantic about this, that the actor function maps spaces to spaces, right? Okay, so we're not talking about point-to-point mapping. We're talking about a functional mapping of spaces to spaces, not a point to a point. Okay? But it turns out that what we can do is we can break it down, instead of function spaces, down to just functions. Okay, so for instance, what you can do is at an nth reaction, so some point down, tick, 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 and n reactions later, there's some function, right, determined by the FSM diagram that maps the input space to the output space, right? That's what it does. That's what the FSM does. It's the update function. And therefore, at each tick, right, when I say tick, I don't necessarily mean time, I mean in reactions, and that's inherently linked in time anyway. But so at the nth reaction, right, that this signal here at that nth reaction is composed of the update function at that reaction point, right? Think about where you might be in an FSM diagram. That's the function that's mapping where you go next. And it's mapping obviously the current value of the signal here. Okay, so what I'm saying here is that back here on this slide, right, we have to consider a mapping of space to space and almost a search over all of that to make sure that this holds. Here, we can zoom in and just look at it on like almost a state-by-state basis, because every state will have a different mapping from here to here. And it's going to give us an idea of how to search for this fixed point. Okay, we can do it essentially state by state and work through, find all of these, and then by implication, you've almost sort of done that. Okay, so apples have to map to apples and oranges have to map to oranges. That's the way it goes. And I'll just go back. We call this function the firing function. Okay, it's like the tick that gets the machine going, right? It's mapping this to this. Okay, so it's important that we have what's called well-formed feedback. And I'll give you two very, very simple examples from digital logic, almost trivial examples. Right, so with this fixed point function here, there's two problems with it. Either the function doesn't exist, so you end up with something that's it's a contradiction, or it's not unique. So you have no way of deciding which one it is. And if either of those hold, we're going to call the system here, this feedback interconnection system, ill-formed, otherwise it's well-formed. And importantly, if there's a state that's not reachable, so think about a state space FSM diagram, if there's an unreachable state there, then we don't need to consider that, right? Whether or not it's well-formed, because you'll never get into that state. All right, so we could eliminate that and forget about that. That'll help us with some searching that we'll do in a minute. So I'll give you a couple of very simple examples that I dreamed up. The classic example would be three inverters in cascade, like that. It's not an FSM, obviously, but we're just looking at whether or not this has a fixed point of operation here. And clearly, well, it doesn't, because if you put 0 in here, you've got 1, you've got 0, you've got 1 and 0 can't coexist, right, as logic. It doesn't make sense. Likewise, if you try 1 on this side, 0, 1, 0, and you get the same contradiction. So no fixed point exists for this particular circuit here. It's an astable circuit, and it leads to metastability and all that those sort of problems there. What about if we do a more complicated example? So the example that I've got here would be a single input circuit. This doesn't have explicit feedback as such. It's got internal feedback. Let's make another output Z. And let's connect these together here. So this doesn't have, it's not an FSM again, but we're just working out if there exists a fixed point for this circuit. How do we determine that? Well, we sort of enumerate over all the inputs here. If X is, what we do first, if X is 0, that's very easy to determine, because we know that ANDing anything with the 0 gives us a clear 0 on the output, so it's got a fixed point. Likewise, if we put X being 1 here, well, in order to determine the output here, if this is 1, we need to know what the other input's doing, and a 1 ORed with whatever will give me a 1 and a 1, and therefore we get a 1. So, funnily enough, Z is just copying X, but it's a fixed point, right? The fixed point exists for this circuit. Okay. Note that we're not, in this case, we're not considering delays and things like that through here, where we could get oscillations and all sorts of weird stuff going on here. Right, I'll give you a more concrete example in terms of an FSM. Here's a very simple FSM, two-state FSM, one input, one output, but it's in a feedback formation here. So what we want to do is we want to check for well-formedness, if you like. And the two rules are that we have to check fixed point if it exists and if it is unique, right, to be well formed. So let's have a look here. Where do we start with analysing this? Good place to start would be the default state. So the trick here is that we're going to start here, and we want to make sure that that whatever's here is compatible with whatever's happening here, right? We can't have incompatibilities. And so in S1, there's two this is my way of thinking about it. There's two transitions here, right? There's a transition if A is present, and there's a transition if A is absent. Now, for both of those transitions, the output is absent. There's no output. It's absent. Okay? So here, in S1, the output's absent. Now, if the output's absent, it actually also happens to be the input A. So if the output's absent, B, it also means that A is absent, and therefore this transition will occur, and very importantly, the output stays absent. Okay? So state S1, basically, we know that the fixed point of this is S is going to be absent. The feedback, remember S is the feedback here, at some particular reaction N. In state 2, we do the same thing here. So we've got two transitions, if A is present or if A is absent. For both of them, we are outputting B, so B is present. Now B is also A, so if we're in this state here, right, and B is present, then it's going to take this transition, and this transition is congruent with what I just said, that B has to be present, right, in order to take that. So this has the fixed point of being present in S2. So both states have fixed points here. They're both unique. So they exist and they're unique, and therefore it's a well-formed state machine. Okay? The behaviour is completely predictable for this state machine. And it means that you can compose this. Remember, we're interested in basically abstracting these things down to the simplest form you can. And abstracting away that feedback loop leaves us just with a little two-state state machine. And all that state machine does is it alternates between the two fixed points, because there's two states here, absent, present, the output being absent or present. And so, so here we've abstracted this down to the guards here are always true. When they happen, it's up to the system, the environment to decide, but absent, present, absent, present, absent, present. Okay, and that's the result of this composition. All right, so that's a well-formed example. Let's do some counter examples here to show you where a feedback interconnection is ill-formed. So let's fail the existence criterion for well-formedness. Right, so it's a very... It looks quite similar to the previous machine there, but so we'll do the analysis again. In S1, both transitions out of here give an absent output. Okay, so B is absent for both transitions. Now, if B is absent, then clearly it's going to cause a reaction because it's also A, and it will react to S2 here, and the output remains absent. So it's making sense. There's no contradiction there. So we get a fixed point here for S1, and that fixed point must be absent. Okay, now the interesting part happens when you're in S2. Now, what do we look at here? Well, this loop back here has the output being present, and this output here has the output being absent. Okay, so if the output is present, so you're in S2, the output is present here, right, then because B is A, you must take this transition which says that the output must be absent. So you have a contradiction, right? And therefore, the composition is ill-formed. So there's no fixed point for this state. Whatever you choose for the output, right, it's going to be contradictory. Just like in my little feedback loop of those 3 NOT gates, right? That's essentially what you got. You've got a contradictory loop there. So it's ill-formed. Doesn't exist. No fixed point for this, tick. No fixed point for that, fail, right? The machine cannot be well-formed. All right, let's fail the uniqueness one. And this, I think that the existence is the easy one. The uniqueness one's a little more subtle. What does uniqueness mean? Well, it just means that you can only have one fixed point. Okay, you can't have multiple fixed points. Otherwise, which one is it? Becomes non-deterministic in some way. So in S1, so this is a very subtle, if you have a look, there's a very subtle change to the state machine here in terms of some of the conditions here, the outputs on the transitions, I should say. Right, so if you're in S1 and if the output, so if the output's absent, right? So, well, you've got absent, you've got present, so there's going to be something funny going on here. So if the output's absent, if you think about it that way, then we take that transition and we move to S2. Okay, so that doesn't seem to contradict things because these are present. You're not contradicting the transitions. That's okay. And if this is present, then you also get a fixed point where you're doing this and you're not contradicting that transition there either. So equally, in S1, you've got 2 valid fixed points where the output is present or absent. So you have no idea what it is. It's one or the other. You don't know which one. You can't determine which one, so it's not unique. It turns out in state S2, you get a unique fixed point, and it happens to be present. And you can kind of see that from looking at the guards here, how the guards are inverted, and the outputs are the same. There's a bit of a pattern here. When we look at completeness, it might make a bit more sense. Okay, so because both states are reachable, right, it's ill-formed. If S1 was unreachable and not a default state or reset state or anything like that, then we would say it was still well-formed, right? You don't consider those unreachable states. All right, so this is kind of the procedure that I was doing. If it looked a bit arbitrary, there was actually a bit of a procedure behind it, and it's called you're searching. Well, you're searching it constructively. Okay, you're searching for fixed points in a constructive manner. So here's your system here. There's your feedback loop. The trick is, what you do is you start with the signal here being unknown. No knowledge about that. And what that means is, that means the inputs are unknown to the system. So you're essentially saying the inputs are unknown. Then what you do is you find out as much as you can about the system acting on the inputs. Now, if they're unknown, there might be a problem. But sometimes it turns out that even if the inputs are unknown, you can still make a decision as to what the outputs are. Okay? So then it can become known. It's kind of this weird setup here, right? And if you then know it, you have a fixed point. Okay, so assume inputs are unknown, if you like. Try and work out the action of this system on those unknown inputs, not knowing what they are. If you can determine the output, then you've known the input and you've got a fixed point. And as I said, that's kind of what I did before. A state machine for this procedure works is said to be constructive. And you can actually test state machines and feedback into connections to test if they're constructive or not. If they're constructive, it's very easy to determine whether or not they're well-formed. Now, it turns out you can actually have non-constructive, well-formed state machines. So these are state machines that fail the constructive test, and that's the constructive test about assuming that you don't know what the inputs are, try and work out what the outputs are, and then it's got a fixed point. So it fails that test, but it's still well formed. It's an interesting conundrum here. So if we've got a two-state statement, it's very simple, just now that the inputs and outputs come from a set of 0 or 1. And if we know nothing about the input here, we can't determine the output. Remember, this is the whole purpose behind this, the constructive semantics here, that if we don't know what the input is, somehow we can look at the FSM diagram, know what the output is, hey, and that's our input, and we're happy. Here, let's look at it. Let's say if we're in S1 here. Let's pretend we have no idea what A is. So we're here, we don't know what A is. So we don't know which transition is going to be taken, right? So we don't know if this self-loop is going to be taken or this transition here. Now, the issue is that for this transition, the output's absent. But for this transition, the output's 1. Okay, so we can't determine, not knowing the input means we can't determine the output, which means we can't do this constructive approach. But we can do an exhaustive search. Okay, so what we can do instead is then, right, it doesn't work for A being unknown. Let's try all possible values of A and see what happens. So, okay, let's try a fixed point, A equals 0. Okay, so we know it's this one here, the output's 1, the output's 1, ooh, no, that's not right, that's not a fixed point. Okay, A equals 1, is that going to work? Well, what's the transition for that? If A is 1, B is 1, no, that's not a fixed point either. In fact, you enumerate all the possibilities for going over A. The only one that works is if A is absent. Okay, so if A is absent, this transition is taken. And it also means the output's absent, hey, which agrees with the condition there. Okay, so you don't have a contradiction there, if you like. So absent, the S, the signal in, being absent is the only fixed point for S1. Okay, so this is a non-constructive machine, which is still well formed, but it means you have to do an exhaustive search. And it's only really possible if the data types of these things are finite sets like this. It's only practical if the data types are small, right? Because if the machine's complex and you've got inputs that can range over big values, right, you have to exhaustively check every one of them. It's a pain. Okay, so this is called must-may analysis. So this is a constructive machine here. What we can do is, and I was alluding to this before, it's like you can kind of look at the structure and know that it's going to be well formed. So here, let's look at being in state S1. We want to find a fixed point for that state, and it's got to be unique. It's got to exist, and it's got to be unique. So if we're at S1 here, we can immediately determine that the machine, well, for this transition, there's only 2 transitions here. And for both of them, the output's absent. Okay? So it may not produce an output. So what we can immediately say that the output's absent. We've no assumptions on A, right? Because both damn transitions have B being absent. So you can see this is right, the constructive technique, right? That because it's constructive, we haven't even had any assumptions on A to determine that a fixed point for S1 is, we've got a fixed point being the output is absent. So in S2, we look over here, look, there's something interesting going on here with the pattern here, that for both transitions, the output must be present, and so it must produce an output, so we can immediately conclude that the output is present and a fixed point for this as well, and it will then take that transition because these two are the same thing. Okay, so there's kind of a pattern, and it might make sense with when you have originally been drawing state machines and you're trying to cover all possible loops, right? You're actually making a constructive state machine by doing that. You are ensuring constructiveness in a way. Okay, so the machine makes sense, it's constructive, it's well formed, this one, so feedback interconnection works and you're not going to end up with contradictions and the thing's going to start going nuts. It turns out that you can apply the constructive semantics for any interconnection. So we've just looked at very simple feedback systems. You've got a very simple signal coming back. Indeed, this is just a pure signal. But you can do it for compositions of multiple actors where you're pulling out those feedback loops and you are combining all of those feedback signals into one vector, if you like, right? You just a tuple, whatever, of those things all stacked up. And you do the same thing, but it's a bit more of a drag doing this. You start with all of them being unknown, right? They're all going to be unknown. Then from the FSM diagram, you look at the firing function acting on these things here. Once you get new information, right? So maybe, for instance, right back to these things here, you didn't even need the input in order to determine the output. You start being able to populate these things. That might give you more information to populate others as you're going around. And keep going until you get no further information about these values. If they're all known, you know exactly what their values are, then you've got a unique fixed point, right? The machine's happy in that state. All these signals are well defined, and it's a constructive machine as well. So a machine that this works for is called a constructive machine. And there are ways when you're designing FSMs to ensure that the transitions are constructive, make a constructive machine, which means it's then good for feedback. Okay, then feedback's okay with that machine. So you are essentially, in a stack up of all these feedback signals here, you're one by one, or you could be doing multiple at a time, but you're eliminating the unknowns, iterating, finding a fixed point. Okay. So any arbitrary structure like that, right? So that's going back to similar to what we had earlier, where we've got some cascade connections, feedback connections. A state machine language. So there's actually languages in order to simulate how these things work. And the languages you may have not seen before, Estelle, things like that. There's actually languages which can describe how these things work. A state machine language that has constructive semantics on top of it rejects any compositions that in any iteration fail to make all signals known. Okay, so because it's problematic having interconnections that are of systems that are ill-formed, a language will go when you connect things up and you have declarations of the updates, right, via FSM diagrams inside here. It will actually say, sorry, can't do that, because it's going to lead to a situation where these feedback signals are not going to be known, right? And remember, when we pull these out, all these signals become feedback signals when you do a side-by-side composition here, right? These all become, even though it doesn't look like a feedback signal, it is. When you pull that down, that's a feedback signal, that one there. Okay, and if that's unknown, that's a bad thing to be happening. Okay, but the downside is that ensuring that your language and your compiler or whatever, your simulator that you want to simulate these interconnections of state machines, assuming that it rejects machines that rejects compositions that don't have these signals being known, means that the opposite can happen, okay? So you could end up with, back to our example here, a well-formed state machine that language that checks for constructiveness would fail. It would say this one fails the constructiveness check, okay? Not knowing the inputs, can I determine the outputs? Fail. But it actually is well formed because you can find a fixed point, particularly for S1. Okay? So exhaustive search has to be done for these particular types of models. So I guess the moral with this is that we want to be building compositions of machines that have these constructive semantics, right? So because it means that it's a very systematic way of checking that it's well formed, because we want to avoid doing some sort of exhaustive search, particularly for crazy models that have massive interconnections on them. Right, so the whole point of synchronous composition is that we want machines to be fully determinate, right? They're all firing on the clock. We have determinate transitions on every state. And we've got the fact that they can be analysable, right? Remember that these models are models of concurrency, right? Things happening at the same time. Those guys are all doing things at the same time. They're concurrently happening. Threads, which give you the illusion of concurrency in some way by rapidly multitasking between instructions on a PC, don't give you either of those things. Okay, they don't give you any sense of being able to be analysable or really being determinate. Okay, and that's the big problem with threads, as we'll see next lecture. So all constructive synchronous programs have unique, well-defined meaning. It means they're predictable. That's what we want in an embedded system, right? Computers, you're running multiple threads. Things get a bit out of hand. The timing goes off. The blue screen of death. Who cares, right? It's only someone's, I don't know, essay or something. But for embedded systems, this is super important because this is controlling the flight control system on an aeroplane, right? We can't have blue screen of death just happen because threads are interacting with each other in a weird way. All right, there are automated tools, as I said before, that can go and do exhaustive search and explore all the possible behaviours. That is not at all possible when we look at the other model of concurrency, threads. That's just not at all possible. The possible amount of search space is just virtually infinite. You cannot systematically explore all behaviours. At least in this setup here, synchronous reactive model, we can explore every possible behaviour and get guaranteed well-formedness of machines, and therefore we know that they will be guaranteed to work. All right, we'll leave it there for synchronous reactive models. Once again, if you're really interested, you could read about data flow models and some timing things later in Chapter 6. That's for the brave, because it starts getting pretty heavy. Otherwise, we'll move on to the other model of concurrency, threads, which is a messy thing and, yeah, for embedded systems, very bad. All right, we'll leave it there.
So I don't
Yeah.
understand why you saying this is ill-formed. Is it so you're saying then S1?
Because of uniqueness, because you can't determine a fixed point. Fixed point has to be unique, right?
So
So
if you don't know what S1 state is in the beginning, then you don't know whether it's picking that or it's picking that. That's why you're saying S1 is fixed.
no, because you can't determine the value of that signal.
Well, you know that if this is a present,
Hang
that
on,
means
hang on, but you don't know what signal this is. So if I gave you this state machine, I said starts in S1. Can you tell me what we call that S? Can you tell me what S is? You couldn't,
because you don't know what A is. Because what
A is S. The point is that you
Yeah.
can't determine uniqueness with that point, right? Because both S being absent and present are equally valid solutions to that.
Yeah.
So would you build a system where there are signals which you don't know what value they are, and you can't predict that?
Yeah.
Would you ever build a system like that? No.
So you just need to know the initial, like if you know the initial state of this, then it's fine.
Initial state.
So if you know what,
You do know the initial state here. The problem is that you don't know what this signal is. It could be either absent or present. It's both. It could be both. Right? The whole point about these state machines is that you know all the values of all the signals at all times. In this case, there's two equally valid solutions for that wire there. Both of them are equally valid.
okay.
Yeah, and that means that you can't. That's not a good system.